Good morning, everyone. Up to now, we have talked about the phase diagrams and of the metals and metal alloys, especially the phase diagrams for this iron and cementite, this phase diagram. And also, we have talked about mechanical properties and applications of metals and metal alloys. And I told you guys metal and metal alloys, and they are the most important materials that have been used in industry. You need to pay attention and to learn very well the phase diagrams and also phase transformation along with the applications of these metal and metal alloys. And today we are going to talk about another material and ceramics. Today we are going to talk about structures and properties of ceramics. And here is today's objective, and we want to learn the crystal structures of ceramic materials. And first, we look at this periodic table. So this is atomic bonding in ceramics. This is the periodic table, and we are familiar with. And first, we know that we want to know the atomic bonding in ceramics, and the bonding and can be ionic and or covalent in character. And percentage of ionic character increases with difference in the electronegativity of atoms. Suppose we have this is we know the ceramics, they are compounds of multiple elements, and so the difference in the electronegativities of these constituent atoms, and they determine the percentage of ionic character. So the degree of ionic character may be large or small. So it may be large or small. As I said, it depends on the difference in the electronegativity of the constituent atoms. And so for example, for this periodic table, and we can see as for this is for this one, okay, this is IFR. This is 0.7. This is the lowest one. And so here, this is F. It is and the highest one. And so this is the difference between these two guys is the maximum, and at least for this current periodic table. And so this is what the difference in the electronegativity of atoms mean. For this is an FR, F, and they have very huge electronegativity difference. So that means the percentage of this ionic the bonding in this compound, if it exists, will have higher this is the percentage of ionic character. Any questions regarding this periodical table? So this is a periodical table was completed by the Russian scientist. The name is Mendeleev, Dmitry Mendeleev. So here is example, calcium F2. This is calcium. This is Ca calcium F2, and they are huge. And silicon carbide is small. The silicon carbide, you can see this is silicon and this is carbide, and they are very small. So percent ionic character for some materials, and so this one can be characterized using this equation. 1 minus exp, this is a factor, and xa and xb. So these two guys are the electronegativity values for the respect for the constituent atoms. And so for this table gives several ceramic materials percent ionic character of the interatomic bonds for these given materials. So this is the percent the ionic the character. You can see this guy is very, very high, about 89, because of the huge difference in electronegativity between the electronegativity value between these two elements. And ceramic crystal structures. We need to know that we have cations. Cations, and they are the metallic ions and are positively charged. Cation, this is one cation. Anion, so the non-metallic ions and are charged negatively. So these two characteristics of the component ions in crystalline ceramic materials and to influence crystal structure. And first one is magnitude of the electrical charge on each of the component ions. So this is magnitude. The relative sizes of the cations and anions. And I want you guys to know and what are these two deciding factors that for this is the crystalline ceramic structure materials that influence the crystal structure. One is the magnitude of the electrical charge on each of the component ions. So when you have some 3 plus or 3 minus, 2 plus, 2 minus, for example, and also the relative sizes of the cations and anions, the size, this is atom size. So these two are deciding factors to determine the crystal structure. The crystal must be electrically neutral. We know that must be electrically neutral. Otherwise, and so this crystal still has a tendency to have this chemical reaction with the neighboring elements if there is a chance. All the cations positive charges must be balanced by an equal number of anion negative charges. So otherwise, as I said, okay, this is the total, they are not electrically neutral, and so this is a crystal still has a tendency and to have chemical reaction with the neighboring elements, and so will pose potential threats and to the environment. So the chemical formula of the compound indicates the ratio of the cations to anions, or the combination that achieves this balance. For example, CaF2, and Ca carries 2 positive charges, and F has 1 negative charges. In order for this guy to be electrically neutral, and so we should have 2 the F atoms, F ions, and to balance the calcium cation. So the metallic elements give up electrons and one ionized. One ionized means so there's a transformation from atom to this is the ion. So cations are usually smaller than ions. The metal atoms, and they are usually smaller than the non-metal atoms. And each cation prefers to have as many nearest neighbor ions as possible. The ions also desire a maximum number of cations nearest in the nearest neighbors. And then stable ceramic crystal structures form when those ions surrounding a cation are all in contact with that cation. So that is the reason the size of this cation and ion, and they are one of the deciding factors to influence the crystal structure. So keeping this in mind, stable ceramic crystal structures form when those ions surrounding a cation are all in contact with that ion. So then we talk about the oxide. is a structure. Oxygen, oxide means the oxygen is one of the elements involved. Oxygen oxide structure. Oxygen ions larger than the metal cations. The close-packed oxygen in a lattice, and usually an FCC. FCC means face-centered crystal structure. And cations fit into interstitial sites among oxygen ions. These oxygen ions. And the factors that determine the crystal structure. We talk about this one. First one, this is the relative size of the ions. So formation of stable structure, maximum the number of oppositely charged ion neighbors. So this we talk about this one. This is unstable. So this is stable, and so this is stable. And I might ask you guys in a quiz or the exam, why this one is unstable? Why these two guys are stable? And you should be able to use your own words to tell me why. Why? Because for this one, so this cation are not in contact with all of these ions. However, on the contrary, for these two guys, this cation is in close contact with all the neighboring ions. So this is the first reason. Second one is maintenance of charge neutrality. And so this is a net charge in ceramic should be 0. This is what I told you. And reflected in chemical formula. This is a chemical formula. For example, this is calcium fluoride. And so this is one calcium element and one calcium atom and two fluorine the atoms. So this is the ion, the 3 ions. So this is cation, and so this is 2 fluorine and ions. So these two guys, and they are contacting each other, and these two guys are contacting this guy also, and this is -1, totally -2. This -2, the balance is this is 2 positive. And so this is a formula, AMXP. M and P values, and they are determined to achieve the charge neutrality. Any questions regarding this slide? And then we talk about the coordination number and ionic radii. The coordination number, what is a coordination number? Coordination number means the number of the atoms that are surrounding another atom. So to form stable structure, how many ions can surround around cation? And so here is radius of cation. This is radius of iron. So this is coordination number, right? And so here, if this is the ratio of these two guys is less than 0.155, the coordination number is 2, and one is this side, one is another side. This is linear. This is a triangle for this interval. And we can have a triangle. We have 3, 1, 2, 3. So 1, 2, 3 ions, 3 ions, and this one, and this cation. For this interval, we can have 4 tetrahedral, right? Tetrahedral. And so this interval we can have 6 octahedral. For this interval, we can have cubic. So this you can see the radius of the cation and iron is one of the deciding factor of the crystal structure. And so for this one, we have ZNS, zinc blende, and zinc blende. This is an example of the crystal structure. And so for this, we can have, this is the sodium chloride. This is the salt we eat every day. And for this one, cubic, for CS and Cl, calcium chloride. This is a calcium chloride. Ionic radii. So this table shows ionic radii for several cation and ions. So cation, positive, iron, negative. And the computation of minimum cation iron radius ratio, and determine the minimum the ratio of cation, and this is the iron radius, and for octa and hydro site. And for example, this coordination number equals 6. And here is a shows how to calculate this as the octahedral. You can see this is a double of this iron radius, and this double of cation radius equals square root 2, and A equals double of the radius of this iron. So we have this equation, and so we have this equation, and then this is the we can get this equation. Okay, get this equation, and then we know that, and the ratio of the two radii, one is for cation, one is another, the other one is for the iron. It equals this. So this one is and shows how to calculate this radius ratio, and the key is that we have this equation and based on this octahedral site. And you can just take a look at this one closely. If you have any questions, feel free to come to see me. Any questions regarding this slide? No question? On the bond hybridization. The bond hybridization is possible when there is a significant covalent bonding, not just the ionic, but also we have this covalent bonding. So hybrid electron orbits form. For example, silicon carbide. So this is the electronegativity value, and of these two guys, they are very, very close. And so we can use, and this the equation we just learned to determine the percentage of ionic character, which equals 11.5. Okay, so this is very, very, very low when compared with calcium fluoride. And then this only 11.5, we know that, and there must be some other bonding, and so that means about 89% is covalent bonding, and both silicon and carbide prefer sp3 hybridization, and therefore for silicon carbide, silicon atoms occupy tetrahedral sites and occupy the tetrahedral sites. So example problems predicting the crystal structure of this the iron oxide. And iron oxide, over the base of iron radii, what crystal structure would you predict for iron oxide? This is a cation, and so this is ionic radius. So this is iron, and so this is the ionic radius. And so this is the iron, so this is the oxide, oxygen ion, this is iron ion, and we can get this answer. Okay, so this ratio is this one. Based on this ratio, and we go back to the table, we can see that coordination number equals 6. So crystal structure is the sodium chloride. And so this seems very, very simple, but you need to understand it first. In the quiz or exam, I might ask you to give me an example. I might ask you guys to solve a problem. I'll give you another compound, ask you guys to determine what crystal structure the compound has. Use the same logic. And then we talk about the rock salt structure. The same concepts can be applied to ionic solids in general. Right? So this is an example. And sodium chloride, the rock salt structure. And for this is a big ion, and this is a sodium. This is a cation, and so we have this guy's radius equals this nanometer, and chlorine ion, and so this guy's radius equals 0.181 nanometer, And then we get this ratio of these two guys have this one. So we can know cation this is an Na prefer octahedral sites. Octahedral sites. We have this called rock salt. And other oxide, magnesium oxide, and this iron oxide also have the NaCl structure. For this one, we already know that when we using example, I use the example to illustrate and how to determine this guy's crystal structure. We know, so this guy have the same structure as this manganese, same structure as this sodium chloride. So AX crystal structures include sodium chloride, calcium chloride, and zinc blend. And calcium chloride structure, we have this, and we also calculate. And so this guy's radius ratio and equals this number. So for this one, and the cubic size preferred. So each of these calcium cation has 8 neighbor of this chloride. And then another one is crystal structure we call the fluoride structure. And the calcium fluoride I have 2 cation in cubic size. We have these kind of examples. Anti-fluoride structure, position of cations and ions reversed. An ABX3 crystal structure is called perovskite structure. So complex oxide BaTiO3. So we have 3 different these ions, and 2 positive and 1 negative. And these are ceramic structures. This summary of some common ceramic crystal structures. We can see FCC, simple cubic, FCC, simple cubic, FCC, FCC. So these are rock salt, sodium chloride, calcium chloride, zinc blend, fluoride, perovskite, and spinel. So these are examples.